The next property of sound we like to look at is frequency. And this ends up being our sense of high pitch and low pitch. And actually the idea of pitch and frequency, that's another one of those ideas that we tend to use interchangeably, but frequency is something like amplitude that a computer can measure, and pitch is something that we perceive, just like loudness was. So we should start using those words carefully. But either way, what it's really related to is how fast the sound is vibrating. And if we use our spring as an example again, if I have a low frequency thing, it would be a pulse, another pulse, another pulse. It's not going very fast. A high frequency wave would have lots of these moving very quickly. Or if we were to look at a transverse wave, we'd have a low frequency or a high frequency. Now, one thing to be conscious of that might not be clear in this demonstration is that all of the principles of sounds are actually completely independent. I can have a high frequency, low amplitude thing. I can have a low frequency, high amplitude sound. And the frequency and amplitude are in no way correlated to the propagation rate. So they're all completely independent. And it would be kind of awkward if they weren't, if you think about it, right? If the propagation was related to frequency, then things that were high pitch would travel faster. If you played a chord, you'd get one note at a time getting to you. It just wouldn't make sense. But it's just important to remember that they're totally independent of each other, which ends up being utilized in a wide variety of ways, and that we can have audio effects that really impact only certain parts of sound. In that we talked about, we have our delay effects, our effects related to propagation, which was our delays and our reverbs. We have our effects related to amplitude, which is our compressors, expanders, gates, limiters. And we also have effects related to frequency. But they don't really relate directly to frequency very much. What they're more related to is timbre. And timbre is the collection of sound at multiple frequencies. We find that only the very simplest of sounds has energy at a single frequency, and that's actually a sine wave. So when you hear the term sine wave, you're talking about energy at a single frequency. But that rarely happens. Every instrument has energy at multiple frequencies. We call it harmonics. You might have heard the term overtones or partials, and that's describing the timbre, or kind of what we might also term the spectrum, which is how the sound actually has energy at multiple frequencies. And we have a set of audio effects that controls that. And you've heard EQ, right, an equalizer. I might say boost the bottom end. Well, in that instance, I have an amplitude that I'm saying boost, that's raise the amplitude, and I'm also giving a frequency, the bottom end, right? I'm saying increase the low frequencies. And that really is an EQ, would do that. Or we can actually fine-tune that term and call it a filter. An equalizer is a collection of filters. So anytime you're going to give an amplitude at a specific frequency, that's going to be a filter, and it's manipulating the timbre. So what is the range of human hearing? If we think of human hearing as kind of limits, the lowest frequency we can hear, we say is 20 hertz. And the highest frequency is around 20,000 hertz, otherwise known as 20 kilohertz. Now, 1 hertz is once per second. So a 1 hertz sound would vibrate once every second. That's actually below what we can hear, and we hear things that vibrate 20 hertz a second is a very, very low pulse, and really it's almost heard as a rhythm in a way. Now, no one can really hear 20,000 hertz, or very rarely can we hear 20,000 hertz. Young children can often, but as you grow older, your high end kind of dissipates naturally. So we find that really the upper end of hearing ends up being around 18,000 hertz or 18 kilohertz. We find that females tend to hear higher frequencies than males in general, so it's a little bit variable, but it's nice to have that just nice round number of the human hearing range being from 20 hertz to 20 kilohertz. And also, we don't hear equally across that entire range. As we start getting to the higher end, it's not like we just stop hearing sound. It kind of gradually diminishes. And as we go to the low frequencies, the same thing kind of happens. And in the middle, there are some variations in actually how well we hear at different frequencies. It's as if our ears were a kind of EQ themselves. And in fact, every piece of gear you get is going to have this kind of frequency response curve. So that's an important characteristic of your microphones you're going to choose, in that they will impose some kind of shape across the frequency response. It's as if they act like an EQ, and you're going to find that across any PC gear you get actually does have that kind of effect, and our own ears also have that effect. So we can see that this idea of frequency and timbre is going to be an important one across everything we do with music production. So again, like amplitude and propagation, I'd like you to bring this into the forums. And some discussions that you might want to start would be about the Fletcher-Munson curves, would be about the human hearing range. Consider looking into psychoacoustics, which is the way in which we perceive sound. Look up the term masking, phantom fundamental, frequency response, and timbre in general. It's a great set of things to discuss, and I hope we can have those discussions in the forums here.